In this exercise, I'm going to show you how to solve a simple truss problem using ANSYS Mechanical. Before I get into ANSYS, I want to discuss what is the mathematical model used to solve truss problems. Truss problems can be analyzed using equilibrium principles, or it can be analyzed using minimization of total potential energy. Most finite element textbooks and most courses in finite element analysis analyze truss problems using the equilibrium approach. Here instead, I'm going to discuss the truss mathematical model using the principle of minimization of total potential energy. Now we're going to get the same answer whether, with either approach. The reason I'm focusing on the minimization of total potential energy approach is that it can be extended to beams and to shells using shell elements, as ANSYS does, so it's more general. A key assumption built into the truss mathematical model is that each bar in the truss can only elongate or contract. It cannot bend. Real bars are going to bend, but we neglect that effect because usually it's a smaller effect than the extension or the contraction, and neglecting the bending greatly simplifies the truss mathematical model. So here's the truss that I have. It has 3 bars, and there's a force applied over here, and there are some displacement constraints over here. With the assumption that each bar can only elongate or contract, we need to model only the midline of the bar. To explain that, let me draw a schematic of a bar. I'll draw a stubby bar. It's not to scale. And let's say that's the midline. Under the effect of the force, now each bar is going to elongate or contract. Let's say this bar elongates, and the midline becomes something like that. I'm exaggerating it. This is all, under the assumption of small displacements. And once we know how much the midline elongates, I can figure out, pardon my chicken scratch, that's where the bar is, because everything's uniform across the cross-section. This means that we need to put in only the midlines when we draw the geometry in ANSYS. And this means that the key unknown that we want to find is the axial displacement. Let me call that D. And actually that you can figure out once you know how much each pin moves. Let's say this pin over here moves over here vertically, and that means that this bar will extend by something like that. Okay, and again, I'm exaggerating the displacement for the sake of clarity. Now, if this pin moves over here, it's also going to elongate this bar, and one has to take the component of that displacement in this direction to get that extension. It's a little bit more complicated. But the essential idea is that once I know each pin displacement in the X and Y direction, I can figure out what the axial displacement is of each bar. And once I know the axial displacement, I can find the strain, because the strain epsilon is just going to be the axial extension divided by the length of the bar. Let me say that's L. And from that I can calculate the stress, sigma, which is just going to be the Young's modulus times epsilon. Because everything's uniform, so this one can easily calculate the stress, which is uniform across the cross-section, and from that one can calculate the force in the bar, because you just take the uniform stress and multiply it by the cross-sectional area. And once I know the force, I can figure out what the potential energy is, and I'll talk more about that in just a moment, or probably in my next video. Which means that once I know each of these pin displacements, I can figure out what the potential energy is. So my primary unknowns are the pin displacements. And I want to find the pin displacement such that the total potential energy of the truss is minimized, because at equilibrium, the total potential energy is minimized. Before we look at how you minimize the total potential energy, let's think about how the potential energy can be calculated from the axial displacements based on analogy with springs. That's coming up next.